All right, continuing on, let's take a look at non-ideal solutions. We have both positive and negative deviations from Raoult's law. So for positive deviation, this occurs when the attractive forces between the solute and solvent particles are less than the attractive forces that are between the solute and solute particles themselves and the solvent and solvent particles themselves. Take a look on page 518 in your textbook. So the dashed lines are for an ideal solution, and the solid lines are for a non-ideal solution. So we see that in this situation, the vapor pressure of each substance by itself is higher, and thus then the vapor pressure of the solution is also higher. When this occurs as well, because the attractive forces between the solute and solvent particles are less than the attractive forces between solute, and solvents, the delta H for this process will be positive. And so this process then is endothermic. Negative deviations from Raoult's law occur when the attractive forces between the solvent and solute particles are greater than the attractive forces between solute and solvent. Take a look again on page 518, this time on the right, letter B. So if this is a case where the attractive forces between the solvent and solute particles are relatively stronger, that means that's going to affect how much of that substance evaporates. And so what we can see here is that less is going to evaporate. We can see that through the decrease in vapor pressure of each substance individually and as a solution as well. Once again, if this is a case where the attractive forces between the solute and solvents are greater than between solute and solvents, then the dissolving process will be exothermic. Delta H, heat of solution, will be negative. Something that's important to know is techniques that we can use to separate the components of a mixture. Distillation is one of those, and distillation can be used in certain situations. We can also use filtration to separate the components of a mixture, and hopefully we'll get a chance to do an experiment in the second semester where we are using a process called chromatography to separate the components of a mixture. So distillation, like filtration, chromatography, is a method of separating the components of a mixture. I don't really like this definition too much. Rather, this is a technique used to separate the components of a solution or homogeneous mixture. So if a heterogeneous mixture, we can use filtration, for example. So there's two different methods within this process of distillation. We have simple and fractional distillation. Simple distillation is used when the solution contains a non-volatile solute, such as sugar or salt, where the solute is not going to vaporize with the solvent. So the process involves boiling the solution. The resulting vapor consists of pure solvent, since the solute is non-volatile. You collect this vapor, so this is a gas. You collect the vapor, cool it, recondense it back into a liquid, and then that liquid consists of just pure solvent. What if your mixture contains both a volatile solvent and volatile solute? Well, the process is a little bit different. We're going to use something called fractional distillation. So starts the same. You're going to boil the solution, but in this case, the vapor that is produced when that solution boils consists of both components, both the solutes and solvents. However, the vapor will be richer, meaning a greater concentration or greater mole fraction in the more volatile component. So more volatile means more easily or readily evaporated. So when you heat up that mixture, that substance that evaporates more easily is going to be present in a higher concentration, higher quantity in the vapor. Take a look on page 519. We see a setup in figure 1413 where you use this fractioning column, it's called. And so basically what you do is you'll collect the vapor. That vapor again consists of both components. Cool it, recondense it, and then heat it up again. Boil it again. Each time you do this, the vapor will be richer and richer in the more volatile component. Eventually, you get to a point where the vapor consists of just that more volatile component, and you have now separated that mixture. So fractioning columns can be used as well. You can read about those in figure 14.13 if you like. On to our next colligative property called boiling point elevation. Remember that boiling occurs when the pressure on the surface of a liquid equals the vapor pressure of that liquid. We just got done talking about how dissolving a solute affects the vapor pressure of a solvent. And so altering the vapor pressure is going to lead to a change in the boiling point of a substance. So according to Raoult's law, the vapor pressure of a solution decreases due to the solute particles being in the way. Again, we saw this on page 515, where those solute particles kind of disrupt the solvent particles from evaporating. And so this is going to lead then to that solution having a higher boiling point. You will have to heat up that solution to a higher temperature in order to get its vapor pressure up to that of the atmospheric pressure. So boiling point of a solution will always be higher than the boiling point of the pure solvent. Now keep in mind, especially if you have a non-volatile solute, as a solution boils, only the solvent will boil or vaporize, and thus the solution becomes more and more concentrated. And because of this, then, as the solution becomes more and more concentrated, the boiling point will continue to rise. So we have a relationship between concentration and boiling points. We'll see mathematically what that looks like in just a second. First, go to 520. We have a phase diagram here. It shows both for a pure substance and for a solution. And so we see that the liquid gas curve for a solution is shifted over to the right, telling us again that the boiling points, those infinite number of boiling points of a solution are greater than the boiling point of the pure solvent. So mathematically, the equation for boiling point elevation looks like this. Where delta T, it says in the notes, is the change in the boiling point. I'm going to reword that in just a bit. Kb is a constant. It's called the boiling constant for the solvent. And then the lowercase italicized m, of course, is the molality, molal concentration of the solution. So as we talked about before, as the concentration increases, that's going to cause delta T to increase as well, which will cause the boiling point to increase. So delta T is not just a change in the boiling point, but better yet, how much the boiling point goes up by. So delta T is not the boiling point of the solution, it's how much the boiling point increases by. Page 521 in your textbook is a table of some substances along with their KBs and normal boiling points. Notice for water, it says boiling point of water 100 degrees Celsius. That's an exact value. So that will have implications on our calculations when we calculate the boiling point of a solution, as I'll show you in just a bit. All right, 14.7, just below that table. Predict the boiling point of a 1.25 molal sucrose solution in example 14.2. Sucrose is a non-volatile, non-ionizing solute. So the boiling constant for water, if you look in the table, is 0.512 degrees Celsius per molal. Take that, multiply it by the molality of the solution, which is 1.25 in this case, and we get 0.640 degrees Celsius. Now, keep in mind, this is not the boiling point. This is how much the boiling point will go up by. Well, water by itself boils at 100 degrees Celsius. So we're going to take 100. Now notice the delta T is expressed to 3 decimal places. And so I'm going to write the boiling point of water to the same precision. Since that's an exact value, if we just write 100, then we may incorrectly give the answer wrong number of significant figures. So 100.000 degrees Celsius plus 0.640 degrees Celsius gives us a boiling point of 100.640 degrees Celsius. All right, practice number 47. Go ahead and pause the video and do that now. I don't think there's anything in particular I need to make you aware of. So go ahead and pause now. So here's our setup. We need to first calculate the molality of the solution. So take the 8.89 grams of sucrose, convert that to moles. Moles of solute divided by kilograms of solvent. So the mass of the water is 34 grams. Convert that to kilograms. We get a molality of 0.765. Take that, multiply it by Kb of our solvents. The solvent here is water, so we're using 0.512 degrees Celsius per molal. And that will give us a boiling point elevation of 0.391 degrees Celsius. Take that, add it to the boiling point of the pure solvent, and that'll give you the boiling point of the solution. Notice it doesn't go up by very much. If you dissolve about 9 grams of sugar in 34 grams of water, which is really not a lot of water, the boiling point only goes up by less than half of a degree Celsius. All right, how about freezing point? How does the freezing point of a solution compare to the freezing point of a pure solvent? It says here that solute particles get in the way of freezing solvent particles. Consequently, the freezing point of a solution is lower than that of a pure solvent. So you need to decrease the temperature by more than what you would normally have to in order to get that solution to form a solid. We can do some calculations with freezing point just like we did with boiling point. We'll see that in just a second. As with boiling, solute particles, though, do not freeze with the solvent particles. Therefore, the freezing point continues to decrease or drop as the solution freezes. So when you have, let's say, sugar water and you freeze it, only the water is going to freeze. So as some of the liquid turns into a solid, there's less and less liquid, which means the concentration of the solution is going to increase, which then means that the freezing point will continue to decrease. All right, it's mathematical equation for freezing point depression, delta TF this time. Like KB, KF is a constant called the freezing constant for a particular solvent. Delta T is how much the temperature will go down by. So decrease in temperature this time. All right, go to 522. Let's take a look at an example. A very similar approach to what we did with boiling point. Read along. It says when 15.0 grams of ethyl alcohol or ethanol is dissolved in 750 grams of formic acid, the freezing point of the solution is 7.20 degrees Celsius. The freezing point of pure formic acid is 8.40 degrees Celsius. Evaluate, that means determine or calculate Kf for the formic acid. So usually we use this equation to find freezing points, the freezing point depression, but this time we're given enough information in the problem to calculate the freezing point depression, and we're going to use that to find Kf. Now notice you're given masses of both components of that solution. Make sure you know which substance is the solute and which substance is the solvent. Sometimes there's context clues in the question. This is dissolved in this. Or, as we mentioned previous lesson, usually the solute is the substance present in a smaller quantity. So in this case, the ethanol is the solute and the formic acid is the solvent. So first thing we need to do is determine the change in freezing temperature of the solution from that of the pure solvent. So 8.40 degrees Celsius minus 7.20 degrees Celsius is 1.20 degrees Celsius. Take that divided by the molality of the solution, so we got to determine that as well. Take the 15 grams of ethanol, convert that to moles. Take the 750 grams of formic acid and convert that to kilograms. And we get a concentration there of 0.435. Divide those, and you get 2.76 degrees Celsius per mole. All right, this one on number 49 on 542 is a little bit different. We're actually calculating the freezing point of the solution. So go ahead and pause the video and do that now. So we determined the concentration already on previous problem, so 0.765 mole. This time we're going to take that and multiply it by the Kf of our solvent being water, the Kf of water. It's 1.86 degrees Celsius per mole. And we get a freezing point depression of 1.42 degrees Celsius. Now be careful with this next step. It does matter how you do the subtraction. Now remember, water by itself freezes at 0 degrees Celsius. And when you dissolve something in water, it's going to lower the freezing point. So it's got to be less than 0. So take the freezing point of the solvent minus the delta T, or freezing point depression, and that'll give you the freezing point of the solution in this case, which is negative 1.42 degrees Celsius. No need to take a look at 14.9. We did one just like that just now, calculating the freezing point of a solution. So instead, go to 542, number 55. Now be careful, this one is a little bit different because the solvent is not water. And so be careful, make sure to use the right constants, make sure to use the right freezing points, or in this case, boiling points rather, and go ahead and work on that problem. So go ahead and pause now. Let's actually change this up. Let's do the freezing point of this solution. So number 55 asks for boiling points, but let's do the freezing point. I believe you have the constants and freezing points that you need to do this calculation. So if you got boiling point, I'll try to get you the answer, but also do freezing point. Go ahead and do that now, please. All right, so I decided to do this one in one big shot here. So took the normal freezing point of our solvent, which is benzene. That's from the table in the book, 5.48 degrees Celsius, minus the delta T for this particular solution. So the first part is calculating the molality of the solution, so moles of the solute per kilogram of the solvent. The Kf for benzene is 5.12 degrees Celsius per mole, and we get a final answer, freezing point of a solution being negative 1.46 degrees Celsius. If you want to break that up into steps, that's fine, but you can do it all in one shot as well if you like. All right, let's take a look at 1410 on page 523. We can use the formula for boiling point elevation or freezing point depression to ultimately determine the molecular mass or molar mass of a substance, and that's what's happening here. So let's read along, please. A 1.20 gram sample of an unknown covalent compound is dissolved in 50.0 grams of benzene. The solution freezes at 4.92 degrees Celsius, calculates the molecular weight of the compound. So let me walk you through this a bit. This is a pretty extensive calculation. So let me just jump to the very end. So we're trying to determine the molar mass of this particular substance, this unknown covalent compound, which is our solute. And to find that, we're going to take the mass of that substance divided by the moles of the substance. Well, I'm pretty sure we already know one of those, like always. So we know the mass is 1.20 grams, so we need to find moles. And so we can do that by first using the formula for freezing point depression. We can use that to find molality. So if we take this and rearrange it to calculate molality, we're going to get delta T over Kf. And then once we know the molality, we can use that along with the mass of the solvent to find the moles. That moles is going to go here. Please do not do this on your test where you're drawing arrows, but actually write the number in. Put that number underneath the 1.20 grams, and you get the molar mass. So taking a look at the solution, that's what they do. Calculate delta T first. So freezing point of the solvent by itself minus the delta T. So we get a freezing point depression of 0.56 degrees Celsius. Take that divided by Kf for benzene. Molality 0.11 molal. We're going to take that, multiply it, right? We're multiplying here. Multiply the molality by the mass of the solvent in kilograms, which was 50 grams. Convert that to kilograms. And we get moles of solute, 0.0055. Take that and put it underneath the 1.20 grams. We want 2 sig figs, it looks like, in our answer. So you get 220 grams per mole, or 2.2 times 10 to the second grams per mole. Technically, the question asks for the molecular weight or molecular mass. So we want units of AMU. So that's why the final answer is given as 220 AMU. All right, it's your turn. Go ahead and do number 61. It's just like this, finding the molar mass. Page 542. Go ahead and pause the video now. All right, so I combined some things again to one setup. So took the mass of sulfur, 0.154 grams, divided it by all of this. So 5.47 is the freezing point depression. It already tells us how much the freezing point goes down by. Divide that by 40.0, which is the Kf for that substance, our solvent, which is camphor. And then multiply that by the mass of the solvent in kilograms. That the whole thing there will give us moles. So molality times kilograms equals moles. And we get a molar mass of 257 grams per mole, or a molecular mass of 257 AMU. One sulfur atom has a mass of 32.1 AMU. So 257 divided by 32.1 is 8. So that means that the chemical formula for sulfur, or molecular formula for sulfur, is S8. There's a couple more examples there at the bottom of the page. I think we will save those for later. If you need more examples, we'll stop here for now and continue tomorrow with electrolytes, electrolytic solutions. Thanks for watching.